Hello, good morning. So today I'm going to tell you the story about visibility of Shafarevich-Tate groups, which is an idea that I learned about from Barry Mazur when he came to Berkeley around I think 97 or 98 and gave a lecture. So he gave a lecture, and usually at these number theory lectures I sort of fell asleep, but at this one I perked up, became extremely excited, and have been very much interested in visibility ever since then. So this table outlines some of the sort of successes in visibility, and by the end of the talk you'll have some idea of what these sort of pieces of phrases mean. And there are still a lot of open questions in this subject. Quite a number of problems haven't been answered yet, and I'll hopefully tell you about some of those as well. So the reason for existence of visibility, I guess initially, well, I asked Barry before I prepared my talk, I said, why did you come up with this idea of visibility? And he said, well, you know, the literature about sort of seeing or constructing elements of Shafarevich-Tate groups is a total mess. So on the other hand, the literature about giving elements of elliptic curves, giving points on elliptic curves is very clean. If you want to write down a point on an elliptic curve, it's a relatively reasonable thing to do. Whereas if you want to write down an element of a Shafarevich-Tate group, it can be really, really messy. So that was the motivation for visibility. And various things have come out of this initial motivation. So my talk will be divided into 6 parts. Part 0 will be a quick introduction. And in that, I'm going to define what visibility means. Fortunately, the definition is extremely easy. Then next, I'll talk about this project, which was, I don't know, the first big project that kind of got visibility going. Then I'll talk about the second one listed, the third, the fourth, and a little bit about the fifth. Okay? So first, the definition. So fix closed immersion of an abelian variety A into another abelian variety B, and this is over a field K. Then the visible subgroup with respect to this embedding of H1 K comma A is, and you might imagine various complicated definitions of what this could be, but fortunately the definition is very simple. It's the kernel of the natural map from H1KA to H1KB. So that's it. So you have an abelian variety A, and it's seen in some bigger ambient abelian variety B, and you just define a subgroup of the first Galois cohomology of A, and it's just the kernel of this map. Now, to motivate why you would call this subgroup the visible subgroup of H1 with respect to this embedding, let's consider the exact sequence 0, A, B, and then the quotient abelian variety C, and then 0. And then pass to the associated, or at least the beginning of the associated long exact sequence of Galois cohomology. So it goes 0, A of K, B of K, C of K. Then you have H1 KA, H1 KB, and so on. So the kernel of the map from H1 KA to H1 KB is exactly the image of C of K under this connecting homomorphism delta. So the map C of K, the map delta from C of K to H1 KA factors through this visible subgroup. In particular, from this diagram, you see that every visible element of H1 arises from a k-rational point of C. So What that means is somehow visibility, well, one consequence of that, because of the Mordell-Weil theorem, since C of k is finitely generated, and this group is a torsion group, this quotient of it has to be a finite group. So the visible subgroup is finite, which is nice, since in a moment we'll consider the subgroup of elements in here that are in the Shafarevich-Tate group. And since the Shafarevich-Tate group isn't known to be finite, it's nice to have a finite subgroup of it, defined in some reasonable way. So that's one observation, finite by Mordell-Weil. And another thing is, as I said, every element here comes from a rational point on C. So it comes from a point P in C via the connecting homomorphism. Explicitly, what this connecting homomorphism does, if you view elements of H1Ka as principal homogeneous spaces for A, you can think about this explicitly as follows. Let's call the map pi from B to C. So the map from B to C, we'll call it pi. Then you can consider the fiber over P. So I'll draw a little picture, put a little box for B, maybe a little curly line for A, and think of C as being like a surface. We have this point P on C. It's a rational point, and you can consider the fiber of the map pi over the point P. That's some sort of coset of A inside of B, so it's a translative A inside of B, and it looks a lot like A, but it need not be an abelian variety. In fact, if the cohomology class that P maps to is not 0, then this fiber, pi inverse of P, won't have any rational points. What it does is it represents this cohomology class, C, that P maps to in the Weil-Chatelet group of A, which is the group of equivalence classes of principal homogeneous spaces for A. So that's one sense in which elements of this nice subgroup of H1Ka are visible. Okay, finally, the visible subgroup of the Shafarevich-Tate group with respect to our embedding of A into B it's just the intersection of this Shafarevich-Tate group with the visible subgroup of H1, or what's the same, it's the kernel of the natural map from, well, the induced map from Sha of A to Sha of B. So that's it. It's the elements of the Shafarevich-Tate group of A that go to 0. So that's an extremely general notion. And I've been told that this sort of idea, considering the subgroup of cohomology classes that go to 0 and something else, is something that's considered in other fields as well. So it's not something unique to arithmetic geometry. Yes? Oh, there's a new one. Ah, great, thank you. Okay, so now let's specialize a little bit and enter into this first section. So I'll call this modularity. And I'm going to put this in quotes of Sha of E. So here's the idea or the question. You have an elliptic curve over Q. So now we're specializing a lot from this general context. And let's assume that the elliptic curve is sitting inside of J0 of n sub E, where n sub E is the conductor of that elliptic curve. So this is, if you have any elliptic curve over Q, then it's isogenous to something that sits inside of J0 of n. And you could ask whether or not the elements of the Shafarevich-Tate group of E are modular in the most naive possible sense, which would be that they're visible inside of J0 of n. So literally, the genus 1 curves that represent these cohomology classes live inside of J0 of n. It's a natural analog of modularity, but for genus 1 curves instead of elliptic curves. So a question, and this was asked by Barry Mazur, and also answered by him, is everything visible in the sense that Sha of E over Q is equal to the visible subgroup with respect to this God-given embedding into this modular Jacobian of Sha of E over Q. Are those equal? Given an elliptic curve, is all of its Shafarevich-Tate group equal? If that were true, for example, we would have finiteness of Sha. It's not true, though, but it's, in the examples, it's true surprisingly often. So teaming up with one of his students, Adam Logan, and also John Cremona, he tried to decide whether or not this was the case, and they looked at elliptic curves of larger and larger conductors. They looked at tables, and I think for curves of conductor less than 2849, it seemed that this might very well be the case, perhaps. But as soon as they hit level 2849, they found an example where there's no possible way this would happen. So they gave an example where they could prove that you do not have equality here. So the answer is no, but in the data, it happens surprisingly often that the answer is yes. That's in the data. It might be that when you consider n several billion, it's very unlikely for this to happen. Yes, Henri? It's around 600. Actually, I have the paper right here, so I'll tell you. So 681. Remember that we're considering only the elliptic curves that sit inside of J0 of n. If you consider all elliptic curves of, say, a given conductor, then you're much more likely to find some with non-trivial Shafarevich-Tate group. If you consider the ones inside of J0 of n, it's less likely that they'll have non-trivial Shafarevich-Tate group. It tends to be that the strong one has a smaller Shafarevich-Tate group than the other ones in the data. Yes? One does not have to assume that for this example. So, I mean, to say no, you don't have to assume that, because for the 2849 example, Mikhail still did a 3 descent on the curve and proved that Sha is really non-trivial. So when Mazur did the computation with Adam, Logan, and Cremona, they had to assume the BSD conjecture to know that there was anything in Sha at all, except maybe at 2. So quickly, the smallest example where Sha should be non-trivial is at level 571 with an element of order 2, and for odd order, 681. So you have to go quite a ways until you see anything. But there's still, a number of examples.
For the ones that are Sha non-trivial, it's still.
Yeah, it's pretty surprising. I wouldn't have expected as much as it occurred. But the answer is no. There are lots of examples where this fails. One example that I'll mention in another context in just a moment, there's an E sitting inside of J0 of 5389. If you use the BSD conjecture, you see that the Shafarevich-Tate group should have order 9, and it's a theorem that it really has order at least 9. But it's definitely not the case that the Shafarevich-Tate group of this E is visible in J0 of 5389. So the next question that you can ask, and unfortunately from a numerical point of view, very little has been said about the answer. So here's the next question. Well, we have E sitting inside of J0 of n, and in general, its Shafarevich-Tate group most certainly is not visible in J0 of n. So why stop there? Why not consider J0 of n times m for various integers m? And I like to call this visibility at higher level. So in other words, is there an m such that Sha of E over Q is equal to the visible subgroup where you've embedded in J0 of n times m of Sha of E over Q. So is everything visible at some higher level? And it doesn't really hurt the question too much if you want to put 1 here. Just makes it more likely that the answer might be yes. But the state of this problem, even after a couple of years of computation, is that I don't think anybody even guesses an answer. So there isn't even a conjecture, one way or the other, about whether or not elements become visible if you stick your E inside of larger and larger J0 of n's. Another closely related question is the following natural question. What is the direct limit of the Shafarevich-Tate groups of J0 of n over all integers n? Or maybe all square.
Is the elliptical embedded in J0?
Yes. Yes. So I don't need to, I'll erase this for a moment. So E is initially inside of J0 of n sub E, and then you map J0 of n sub E in some way to J0 of n times m.
And then no kernel here.
There may be a small kernel, but it's well understood in terms of the...
It's no more the elliptical, it's an exogenous elliptical that you take over.
Yeah, if you want to be very careful, and you do, then you should make this slightly more precise when the map is not injective. So for example, you could ask that the cohomology, that for each cohomology class C in here, when you consider the image elliptic curve here, that cohomology class has the same order, and moreover is visible in J0 of n times m. Okay, but for example, well, if m is say a prime, then you can embed this by, I think, the sum of the two degeneracy maps, or the difference of the two degeneracy maps, and then you can really completely understand the kernel. And as long as the m torsion of E is irreducible, it's going to be injective on E, so you don't have to worry about that. But that's a technicality that you'll deal with if you actually try to think about this problem seriously. So here's an example. Let's take this elliptic curve again. I'll call it, well, I'll circle it. So that E of level 5389, then it turns out that there's a map from E into J0 of 7 times 5389. The kernel has order of power of 2, and these elements of order 3 become visible here. So this is an example of visibility at higher level. So Sha of E over Q square brackets 3 is visible in J0 of 7 times 5389. But it's a question, and the answer is very unclear, even from the data. I really have no idea whether or not the answer should be yes or no. And the question's been around a long time, so, or I mean by my standards, 3 years. Okay, so that's the situation for modularity. One other question is, what about visibility somewhere? And that gets into the second section. So here, instead of asking for visibility inside of J0 of n, or inside of J0 of n times m, you just start with an element of Sha, or of H1, and say, is that element visible in some abelian variety? I.e., can you embed your elliptic curve in some ambient space such that under the induced map on cohomology, the element goes to 0? So you have an E, and you want to see whether or not you can embed it somewhere. The first version of this question was the following. Given an E and an element of its Shafarevich-Tate group, can you embed E in an abelian surface, so a two-dimensional abelian variety, so that that element of the Shafarevich-Tate group is visible? So given C and Sha of E, is there such an embedding with dim B equals 2, such that C is visible in B. And to make things a little bit simpler and to help in explaining the answer, let's assume that C has order P. So it's a prime number P. So this question was asked by Mazur, and the reason I think that he asked it was that in this situation, the quotient of B by E has dimension 1. So B is made up by gluing together two elliptic curves along a finite subgroup. So if this were true, or when this is true, you have a better chance of really understanding this element of Shaw, because it's visible somewhere in an abelian variety that must be very easy to understand, since it's just made up of elliptic curves. No abelian varieties are anywhere in sight. And it turns out that the following so far. So if P is 2, the answer is yes. So when P is 2, there's an abelian variety B of dimension 2, so that elements of order 2 are visible in it. And this is due to Thomas Klinke and myself. When P is 3, the answer is also yes. In fact, this was done first. And this is due to Mazur. And his argument's really nice. What he does is he takes x of 3 and the universal elliptic curve over x of 3, and then twists it twice and constructs a moduli space that somehow classifies the possibilities for these B's, and notices that it has infinitely many rational points. So it's just a hand wave description of his proof, but what he gets is lots and lots of B's that are surfaces so that our element is visible. Notice that there's a connection between this question and the previous question, namely visibility at some higher level. Because this B is made up of elliptic curves over Q by gluing along some torsion, since it's a two-dimensional abelian variety that contains an elliptic curve. And we know by the theorem on my t-shirt that every elliptic curve over Q is modular. So this B is isogenous to a piece of some J0 of n times m. So it might be that these two theorems imply a yes answer to this question for elements of order 2 and 3. But there are some subtleties there. Namely, how exactly does B, if it sits at all inside of a J0 of n times m, how exactly does it sit in there? You might have to think about multiplicity 1 type questions. And apparently nobody has really thought that through. So here's an open problem that's certainly doable. Do these facts imply a yes answer to the question? I'll call this question star. So there's a question for you. Okay, P equals 5. That's completely open as far as I know. Maybe everything's visible in an abelian surface, maybe it isn't. So open. And P sufficiently large, I would definitely conjecture the answer is no. Because if you have a large P, like P equals, 389, and you have two elliptic curves that are non-isogenous, and they have the same 389 torsion, then you have a point on a certain object that shouldn't have any points for a P sufficiently large. People haven't found examples of pairs of elliptic curves that are non-isogenous with the same P torsion for P very large. Ernst Kahne studies this question a lot, for example. But certainly the wisdom is that the answer should be no here. But as far as I know, there's not a single example of an element of a Shafarevich-Tate group where somebody's proved that it's not visible in a surface.
Is the answer no a theorem, or is the answer no a guess?
Wait, the what? Sorry.
When you say it's no, you have a counter in that?
It's a conjecture.
Okay.
Yeah, sorry. In fact, there's not a single counterexample for any p. It's just a conjecture. Sorry for my handwriting. Okay, more generally, if you take, and here's a nice fact, if you take any abelian variety over any field, then there always, and any element of its first Galois cohomology, then there always exists a bigger abelian variety that contains it, so that element is visible. There's a restriction of scalars construction that gives you this bigger abelian variety. And you can use that to deduce the p equals 2 case of this answer. So proposition, given any A and C in H1KA, there is B that contains A such that, or with C in the visible subgroup with respect to the embedding of H1KA. So everything's visible somewhere. There's no restriction on the dimension of A or the base field.
What is the dimension of B?
Sorry?
What is the dimension of B?
This doesn't say, but it's at most let's see, it's at most the order of C to the power of 2D, where D is the dimension of A. Okay, so you can give an a priori bound. Well, I'll just show you the proof. The idea of the proof is very, very easy, and you'll see what the dimension is from that if you know a little bit about Galois cohomology. You just take your element C in H1KA, and this is continuous group cohomology. So there's a finite extension of K, finite Galois extension of K. Well, I don't need a Galois extension. There's a finite extension of K. Let's call it L, where this cohomology class reses to 0. It restricts to 0 in that extension. Okay? So basic fact about Galois cohomology. Now, using the Shapiro lemma, you can see that there's a canonical isomorphism between H1LA and H1K, and then the abelian variety is replaced by A is replaced by the restriction of scalars from L down to K of A viewed as an abelian variety over L. So, I mean, I could give you a reference for the details. And then there's a natural map like this, which is induced by the embedding, the natural embedding from A into the restriction of scalars from L down to K of A sub L. And this map, of course, sends C to 0. And so the answer to your question, a bound on the dimension of B is the same as giving a bound on, well, via this construction, a bound on the dimension of the B that comes from this construction. Here's the B, is identical to giving a bound on the degrees of extensions where the cohomology class splits, which is a well-understood question, but could be more well understood. Okay, so that's everything I want to tell you here. Okay, next, Mahmoud Agashe and I did the following. We, I wrote a program in Magma, which is a computer algebra system, that allowed me to list every new form F in S2 gamma 0 of n. For n up to and including 2,333. So actually, I went a little bit farther, but I'll do some subsequent computations that I stopped. For some reason, I decided to stop here. So we listed every one of these new forms, and we found that there are, I think, 19,608 of them. So up to Galois conjugacy. So 19,608 up to Galois conjugacy. And to each of these, as Osterle discussed and other speakers have discussed, there's an associated abelian variety, often denoted A sub f. And what we did was we tried to compute the order of the Shafarevich-Tate group of A sub f as predicted by the conjecture that's the subject of this conference. But that's not such an easy thing to do when you start with an abelian variety. If you start with an elliptic curve, we don't even know an algorithm to do it. But in practice, we can do it. If you start with an abelian variety, computing the conjectural order of the Shafarevich-Tate group, well, it's extremely hard in general because you have to compute everything else in the formula. And one of the things appearing in the formula is the regulator. So, giving an equation for the abelian variety seems to be the only way I know to even hope to get at the regulator. And you can't, I don't know how to do that for abelian varieties of, say, dimension 57. So we have these 19,608 abelian varieties A sub f. And just to remind you, A sub f for me today will be J0 of n modulo I sub f, J0 of n, dual, sitting inside of J0 of n. And here, I sub f is the annihilator in the Hecke algebra of the new form f, where, as you recall, T is the ring generated by the Hecke operators, and that's inside of the endomorphisms of S2, where S2, I just mean the cusp forms. So these are the abelian varieties I'm talking about. And there are this many. So we restricted to a certain subclass of them where we had a better chance of computing the conjectural order of the Shafarevich-Tate group. And of course, the reason for doing that is that once you can compute the conjectural order, you can maybe try to find a counterexample to BSD, or not. So here's the class we restricted to. We considered just the A sub f with analytic rank 0. So the L series attached to A sub f is not 0 at 1. And by results of Colley-Wagen, Gross, and Zagier, mainly Colley-Wagen, using Euler systems, you know that, and also Logachev, so the A sub f is not an elliptic curve. So these guys wrote 2 papers that deal with this situation. You know that A sub f of q, the rational points, is finite, as is the Shafarevich-Tate group of A sub f. And in theory, you might imagine using their proof to give an upper bound on this Shafarevich-Tate group. When it's an elliptic curve, that's reasonably easy to do. For abelian varieties, they discuss the possibility of doing that in their paper, but I don't think anyone's done it for any examples at all. So we get these, and then for these, you can use modular symbols and other techniques to compute things like Tamagawa numbers and special values of L functions and quotients L of 1 over omega sub a. You have to worry about things like Manin constants. It's kind of a hugely complicated business. But in the end, here's what we found. BSD predicts, so Birch and Swinnerton-Dyer conjecture predicts that the odd part of the cardinality of the Shafarevich-Tate group of A sub f over q is definitely bigger than 1. It's divisible by some odd prime for at least 168 of these. Okay, a couple of those are elliptic curves, but a lot of them have dimension 20, dimension 30. They can be quite big. And there may be a few more than 168. But what we did was we computed a lower bound, and in some cases an upper bound, on the conjectural order of the Shafarevich-Tate group. So here I said BSD, so it's okay. Okay, now the question is, for these 168 abelian varieties, can you prove that there's something in the Shafarevich-Tate group of the predicted order? And we used visibility to do just that in some cases. Sorry, I couldn't hear the first part of your sentence because the blackboard was shaking. I couldn't hear the first part of your sentence because the blackboard was shaking. We compute an upper bound on the torsion. And so let's see. Let me just recall the formula so it's clear. We also compute a lower bound. And if those meet, then you get the answer. If they don't, then let's see. So this is, well, so you have that. So we compute a lower bound by computing the order of the image of the cusp 0 minus, well, of the thing 0 minus infinity. That gives a rational point on A sub f. You can compute its order using modular symbols. And that gives a lower bound on each of these numbers. Well, at least on this number. And that certainly gives you a lower bound on the cardinality of Shaw. In many cases, though, you can get an upper and a lower bound. Is that sufficient? So in general, we don't compute really anything exactly, but we get lower or upper bounds as the case may be. So you need lower bounds on this, you need upper bounds on this, and so on. You need bounds on this in order to get a lower bound on this.
You only use 0 minus infinity, not the full plus middle subgroup.
In this experiment, in order to get this number 168, we only use 0 minus infinity. Though I do know exactly how to use more cusps, and I know exactly which ones at least are rational in J0 of n, because it's in Glenn Stevens' thesis. But yes, I used only 0 minus infinity to get these 168. You might go home and use more and get a slightly larger list. There's definitely a lot of room for incremental improvement in algorithms for trying to compute various quantities in this expression. For example, when p exactly divides the level, you can do pretty well for computing the Tamagawa number. But when p squared divides the level, it's kind of subtle because you have additive reduction. But on the other hand, then there are nice a priori bounds on the size of the Tamagawa number. Okay, so let me show you in one example, the first example, how you can deduce that the Shafarevich-Tate group of one of these is non-trivial in a case when we're capable of doing that at present. So here's an example. So consider the Jacobian J0 of 389. Here 389 is a prime. And if you look inside of it, you'll find the first elliptic curve of rank 2, coincidentally. And more importantly, you'll find one of the a sub f's in my list of 168 a sub f's that definitely have conjectural, non-trivial odd part of their Shafarevich-Tate group. So inside of that, you find an abelian variety a sub f, and it has dimension 20. And as I mentioned before, the lowest conductor elliptic curve of rank 2 is also sitting inside of J0 of 389. And we're going to use it as a handle to produce some visible elements of the Shafarevich-Tate group of a sub f. And these visible elements will sort of give you the part of Shaw that's predicted to exist by the conjecture of Birch and Swinnerton-Dyer. So that conjecture says, if you compute various quantities up here, it turns out that, so there's only one C. Actually, it would be nice to have an example like this for this conference. So I'm going to take this equation and recopy it over here, but replace each of the things by a number, which is the number I computed, when possible.
What's the answer? J0 of 389?
32. So it divides up into a +1 and -1 part because of the action of the Atkin-Lehner involutions. And the +1, the part where Atkin-Lehner acts as -1 is filled up by E and A sub f. and they completely fill it up. And the other part consists of, I think, 3 abelian varieties that together make this up. They have dimensions 2, 3, and 6, but they're completely irrelevant for this example. So I don't know this thing yet. The torsion subgroups each have order 97. So this is a particularly simple situation. You get upper and lower bounds of 97. And over here you get, oh yeah, sorry, left off the Tamagawa number. It's also 97. By the way, it's a nice theorem that this Tamagawa number cancels with the order of this torsion subgroup at prime level that Matthew Emerton proved. So you get this, and then over here you get 5 squared times the power of 2 divided by 97. So you can guess that SHA should have order divisible by 5 squared. And I mean, just from this number, you already guessed that SHA should have order divisible by 5 squared. But you have to work harder to figure out what's going on with the Tamagawa number and so on. But you do work harder and you figure it out. And you get that SHA should have order divisible by 5 squared. So BSD says that the cardinality of SHA of A sub f should be 5 squared times the power of 2. The reason that there's a question mark there, and I don't know the exact power of 2, is because of subtleties involving the Manning constant, an analog of the Manning constant. So remember, Basidix-Hoven talked about the Manning constant for elliptic curves during his lectures, very, very briefly. So, anyways, he talked about it, and there's an analog of it for abelian varieties of dimension greater than 1. And unfortunately, for abelian varieties, it's really hard to compute it. So I don't know how to compute the Manning constant, unlike for elliptic curves, where there's an algorithm which will tell you what the Manning constant is. So I don't know how to compute it. But fortunately, you can generalize an old theorem of Mazur to prove that if the level is square free, then the Manning constant's a power of 2. So you can prove some results like that at least deal with it somewhat. OK, so we get that. And the question of the day is, does 25 divide the order of the Shafarevich-Tate group? And the answer is yes. And you can deduce that from this diagram as follows. It takes a lot of work, but I'll show you the idea of the argument. What you do is you compute the intersection of E and A sub f inside of J0 of 389. This is a computation you can do purely after base extending everything up to the complex numbers, and then using the classical description of this Jacobian as a tangent space modulo some homology. And you have actions of Heck operators on the homology. So you can see everything very explicitly over the complex numbers. And then you can compute the intersection, and you find that it contains all of the 5 torsion of E. It's actually a little bit bigger than that. It has, I think, the 4 torsion of E as well. That's the exact intersection. But it contains all of the 5 torsion of E. And so you can now fill this diagram out a little bit. Let's let C, again, be the quotient of A sub f by this thing. And note that the map from E to C factors through multiplication by 5 because, well, look, it has the multiplication by 5 in its kernel. So you have that. And now all you do is you take this diagram and then look at the Q points everywhere and extend it a little bit using the beginning of the long exact sequence of Galois homology. And then you chase some diagrams. You study chapter 7 of Bosch Luckenbaum right now's book on neuron models. And you eventually conclude that E of Q mod 5E of Q injects into the visible subgroup of the Shafarevich-Tate group of A sub f with respect to our embedding into J0 of 389. So you get this by taking cohomology and chasing exact sequences and then looking at very subtle properties of exactness properties of sequences of abelian varieties when you consider the corresponding neuron models. So it takes a while to write everything down, but in the end you get this. So let me show you just the first step, which is to go from this diagram to a diagram that almost involves an arrow like this, but not quite. So just the first step. All I'm going to do is take q points of everything over there, and then extend things ever so slightly. So first, E5, turns out there's no 5 torsion at all defined over q, so that's just 0. I'm just recopying but taking q points. That's all I'm doing. Here, I'll put E of q. Then multiplication by 5 to E of q. Okay, the co-kernel of that map is just E of q mod 5 E of q. And now I'm going to do the same on the bottom, but I'm going to compress things just a little bit. So just copying it straight over, the map going down goes to, goes to J0389 of q, then to C of q. And I'd really like to have a 0 here, but I don't. So what I'll do is I'll just replace this by J0 of 389 modulo of q modulo a sub f of q. So that's the only little thing I did. Okay, so far so good. Now you have this map, and finally the co-kernel of the map from J0 of 389 of q to C of q is the visible subgroup of H1 q comma a sub f. And that's surjective, out of space here. Okay, and you get an induced map like this. You can use the snake lemma to see that this map is injective, and then the subtlety comes in showing that instead of just mapping into H1, it maps into something. It maps into classes that are everywhere locally trivial. It maps into SHA, but you can't show that. Do you have a, no? Okay. So that's the idea of the argument. And it generalizes. It's not something special for this. You can just sort of delete all the specialness of the letters, and you write down a general theorem over a general base field, which says that if you have 2 abelian varieties embedded in another bigger abelian variety, and their intersection has a certain property, and various other technical hypotheses are satisfied, then the Mordell-Weil group of 1 maps into the modulo something maps into the Shafarevich-Tate group of another. There's also an analog of this when both of these are elliptic curves. It's very clean and even works in some cases for 2 torsion that, that Barry Mazur proved using flat cohomology. So we did this, and we succeeded in showing that the order of the Shafarevich-Tate group is as big as predicted. The order of the odd part of the Shafarevich-Tate group is as big as predicted for 37 of these 168 abelian varieties. So we did it for 37 of them. Of six of those were elliptic curves, so those were already done, and the rest were new. And we could have done a lot more if it were known that if L of AF1 equals 0, then A sub f of q is infinite. But that's not known in general. That's sort of the very, very hard direction of the BSD conjecture. So the abelian subvarieties that we use to construct points in the Shafarevich-Tate groups have to have dimension 1. Otherwise, we can't show that they have points, even though the BSD conjecture predicts they should. OK, so that's 3. So if you lost me at all, don't worry, because we're starting a completely new thing now. So you'll remember in Jan Nekovar's talk yesterday that, well, he mentioned that Castles proved long, long ago that Shafarevich-Tate groups of elliptic curves have order of perfect square. He listed certain numbers, and they change by, their parity doesn't change. So certain Shafarevich-Tate groups have wonderful squareness properties. So this section's entitled non-squareness properties, so non-squareness of Shaw. Okay, so a couple of days ago I was talking to Samit Dasgupta, about this non-squareness, and he asked me, is there any reason to think that SHA should have order a perfect square? So when I started studying abelian varieties, I thought that SHA for a general abelian variety, A, over, let's just say a number field, so that my quote will, I thought that if finite, this group should have order a perfect square. Because for elliptic curves, it's a theorem that that's true. And if you look in this old paper from the mid-60s by Swinnerton-Dyer, so it's Swinnerton-Dyer 1967, then you find an interesting quote that will certainly convince a beginning grad student. So he says, on page 149, it is conjectured to be finite, and Tate has shown that if it is finite, its order is a perfect square. So that makes you think maybe its order would be a perfect square. So if you look at the papers of Tate, like a certain seminar Barbaki he gives, he discusses this, but he certainly doesn't prove that the order is a perfect square. He does remark, though, that for Jacobians, the order should be a perfect square, which led to this paper in the Annals, 1999, by Bjorn Poonen and Michael Stoll. So in December of 1996, Michael Stoll implemented an algorithm of Bjorn Poonen and Ed Schaefer for computing two Selmer groups of Jacobians of curves. And Stoll was sort of surprised because he found one where the two Selmer group had order 2, the Mordell-Weil group was trivial, and so the only possibility would be that SHA has order 2. So he wrote an email to Bjorn Poonen and said, there must be a mistake in your algorithm, so your published algorithm. And Bjorn wrote back and said, well, there can't be a mistake, and I'm sure we better figure out what's going on here. And I'm quoting from the email, we better figure out what's going on here because I'm sure that we'll discover something interesting. And then in parentheses he says, and we definitely won't discover that SHA has order not a perfect square. Exclamation point. So if you look at another email he wrote about a month later, he says that people slightly misremembered, and of course Nekovar got it right in his talk, but there's a pairing between SHA of A and SHA of A dual, and you have to be careful in distinguishing. So if A and A dual are canonically principally polarized, say A is a Jacobian, then this pairing, well, you have to distinguish between it being alternating or skew symmetric. Those notions are different at 2. So it turns out that you can find examples where the Shafarevich-Tate group of a Jacobian has order 2. In fact, if you look at these A sub f's very closely, I think the first example of an A sub f with non-trivial SHA is an A sub f with SHA of order 2. It's kind of funny, but the lowest, first, simplest example. So anyways, they wrote a paper in which they studied the case of Shafarevich-Tate groups of order twice a square. It's a very nice paper. And something I did recently using visibility, I was trying to construct visible Shafarevich-Tate groups by making exact sequences of the following form. 0 E of Q mod P E of Q. I'm sort of jumping the gun. Let me stop for a second. So, oh no, I guess that's okay. Yeah, so I was constructing abelian varieties A and elliptic curves E so that there's a map like this. So a map from E of Q mod P E of Q into the Shafarevich-Tate group of the elliptic curve. So here, this abelian variety A is got by taking E and considering it as an elliptic curve over a certain abelian extension of Q, and it's kind of technical describing exactly which ones I choose, and then taking the restriction of scalars back down to Q. So I get an abelian variety, it's not quite A yet, but I get an abelian variety B of dimension equal to the degree of this extension, and it's equipped with a trace map to E. If you consider the kernel of this trace map, that's an abelian variety A. And that abelian variety, if you base extend up to K, or even up to Q bar, you'll see that this is just a product of copies of E. So A is a twist of a product of copies of E. It's a twisted power of E. And it's equipped with, if you make certain hypotheses on K, then you can prove that there's an injective map from E of Q mod P E of Q into the Shafarevich-Tate group. So unfortunately, there's a hypothesis that has to be verified. For a given P, you have to check something. And I conjecture that it's always true, but you have to check something. So that's why in a minute I'll put a bound on the P's that I consider. But you get this sort of construction. You can make an abelian variety, which is just a twist of a power of E, that whose Shafarevich-Tate group contains model V of the elliptic curve mod P times it. So then I did a funny thing. I took an elliptic curve of rank 1, and I did this. So I got this natural subgroup Z mod PZ inside of the Shafarevich-Tate group. And then I thought, OK, SHA has order of perfect square. I should find the other subgroup. Or somehow, the kernel, there's some sort of pairing mate. I mean, if it has order of perfect square, there should be another subgroup in there of order P that isn't that subgroup. And I couldn't think of one. So what I did instead was I proved that, again, under appropriate hypotheses that I'm not stating, but I can give you a preprint if you want, the cardinality of SHA of A over Q is P times a perfect square. So it's finite, and it has order P times a perfect square. So, yes?
What is P?
Oh, OK. I make this construction for each P up to 25,000. So let's see. There exists, let's see, let me be precise. So for each odd P less than 25,000, there is an A such that it's constructed like this, and it has the property that its Shafarevich-Tate group is P times a perfect square.
This A is not a principally polarized.
You're right. It's definitely not principally polarized. I think if you take the GCDs of the degrees of the polarizations, you'll probably get P. In some cases, that's been checked. So that's what this is about. I think it's P. I think it's P. I know for one example that it's P, for P equals 3.
What are the K's?
The K's, well, there are abelian extensions that correspond to characters of conductor L in order P. So, I mean, I'd have to, it's 2 talks to describe all of this. But OK, so the moral of this is just that, in fact, the Shafarevich-Tate group need not have order of perfect square. So watch out for that, and don't think it should. OK, so that's 4. And then for 5, I'm out of time, basically. The idea here is that, so in doing a lot of these computations, you don't write down equations because it's impossible. Here, A sub f is a 20-dimensional abelian variety. The only way you can really compute very much about it is to play around with modular symbols, with homology groups, and chase sequences, and use subtle properties of neuron models and so on. You cannot reasonably hope to write down equations for something like that, since the dimension's so large. So you start developing technique for computing with such objects. And I went to a conference in Durham, and I heard Birch say that, sort of command people to come up with a theory for computing with motifs attached to modular forms. So if you have a new form f of, say, weight 4 on gamma 0 of n, then Scholl constructed an associated Grothendieck motif. And you can ask to do very similar things. You have to play around with cohomology groups instead. But there are similar constructions, and you get evidence for the Bloch and Kato conjecture from these constructions. So that's what the 5th bullet is about. So just to summarize, visibility allows you in several different contexts to construct subgroups of Shafarevich-Tate groups in situations where, like here, I have no idea how I would do it otherwise. So maybe it gives a little more evidence for the conjecture of Birch and Swinnerton-Dyer. And I didn't find any, I didn't construct any subgroups that shouldn't be there, even though I looked a little bit. So maybe the conjecture is true. even for abelian varieties. Okay, so thank you.